Good morning, everyone. Thanks for joining us today. My name is Albert Pashkowiak. I'm with OACETT, Ontario Association of Certified Engineering Technicians and Technologists. Today's discussion on Transpod and Hyperloop technology should be an interesting one. We're excited to get this underway. Just to note, there will be a poll at the end of the presentation, so look for that once everything is complete. If folks can keep their microphones muted throughout the whole program, that would be great. And if you have any questions, save them for the end, and we'll do our best to answer them. Again, thanks for joining us today on the presentation of Hyperloop technology as presented by the folks from Transpod. Just wanted to say thanks to Lawrence Robitaille of the Renfrew chapter of OACETT for putting this together, as well as the folks from National Engineering Month for making it possible. A big thank you, however, goes out to Thierry and his team at Transpod for presenting today. Their presentation is full of interesting information, and I'm sure you all enjoy it. Before we get into that, though, I'd like to just chat a little bit about OACETT and play a short video. Essentially, OACETT is the Ontario Association of Certified Engineering Technicians and Technologists. So OACETT is a non-profit professional association. We have approximately 25,000 members, and we span about 15 different engineering technology disciplines. Our association advocates on behalf of technologists across Ontario. They work diligently to maintain the certification process for the organization, and they provide networking opportunities to our members as well as professional development, continuous professional development. I joined OACETT in 2008, and I've been volunteering with them since. So I'm the Kingston chapter secretary and also the vice chair for the Young Professionals Committee. So without further ado, if you have questions about that at the end, I'd be happy to answer them. But I'd like to just play a quick video for you, and then we'll jump into the presentation. Let's see if I can share my screen here.
Why are you more qualified than other candidates?
Well, first, I'm OACETT certified.
OACETT certification. Tell me more.
Well, actually, we are...
What is OACETT? We are the professionals who design, maintain, and repair the electronic equipment that makes our world so incredible, and so much more.
We are the experts who make advanced products that touch every aspect of your life.
We are the professionals who help your company save time and money with our experience and expertise.
We are the professionals that plan, design, and supervise the infrastructure that makes this province and economy successful.
We are the engineering technicians and technologists, the part of a skilled team that builds a community in which you live in.
We are professionals who are passionate about the environment by providing services including sampling, modeling, and assessments, all in an effort to protect this great province of ours.
When can you start?
Thank you. So when you ask, what is OACETT certification? I say we are.
We are.
We are.
We are.
We are.
We are future ready. Our certification?
Your success.
Great. Okay, so like I didn't want to stop. So I'd like to introduce Thierry Bautier from Transpod. He's been working in North America, Europe, Africa, and Asia mainly for Caterpillar, I think. And that was before moving to Canada and joining Transpod. And he is the procurement and supply chain director over there. He owns 2 master's degrees in general engineering and business management from Central Lyon and EM Lyon in France. Thierry, take it away.
Yep, thank you very much, Albert. Hello, everyone. Big thank you also to OACETT and National Engineering Month people to organize this kind of event. We're always proud and happy to share our work, our knowledge on Hyperloop technologies. Thank you for your interest. And so I'll be starting today presenting Transpod, an overview of who we are, what we do, what is Hyperloop. And then we'll dig into more details with Dimitri, who's going to talk about his equations, simulations. Augustin is our design director. He will introduce you to industrial design, how to design the transport of the future. And Kyle will join us in a few minutes. He's the hands-on guy. He's doing all the experiments in our office. So he will show you what he's working on. I'm going to share my screen. I have a PowerPoint presentation for you. Okay, are you all able to see the screen?
Yeah, we see it.
Perfect, thank you. So Transpod, we are the Canadian company developing Hyperloop technology. Hyperloop technology, you probably know by now what it is. It's a common name for tube transportation or vacuum train, vacuum tube transportation. There's several names. Since 2012, it's been renamed by Elon Musk as Hyperloop. We like to call Transpod a new Hyperloop system. It's further developments that was the Hyperloop was initially described in Elon Musk's documents. And we're very proud to be the only Canadian company working on that. So there are a few companies in the US, two competitors in the US and a few ones in Europe. Our main purpose is broader than just developing a new technology. It's fun, it's nice, it's fancy to develop a new technology, but we have a major goal behind that is to be able to connect the people in distant cities, major cities, in a better way than what we have today. Today, especially in Canada, we have diesel trains or airplanes, which we all know are very high polluting means of transportation. So we are aiming to be able to transport people and cargo with something that's sustainable. How it works. It's, let's say, not that complicated to explain. It's more complicated to make it work. It's made of two tubes, one for each direction. Inside each tube, we have small vehicle. That's very important, and we'll discuss that later. The vehicles are 25 meters long. They can allow for 25 to 40 passengers, and they are levitating thanks to electromagnets in the tube. And in the tube, we also remove the air, most of the air. The pressure is very low. It's about the pressure that you would find at 40 kilometers above ground. And thanks to very low air pressure, we don't have much aerodynamic friction. There's no contact with the tube as well because it's levitating. So all of that helps us to achieve very high speed. So we're talking about 1,200 kilometers per hour as a top speed for now. It's just below the speed of the sound. And that's the maximum speed. As an average speed, we're talking about 800 to 900 kilometers per hour, which is quite similar to the speed of an airplane. But that's where it's much better to an airplane, is that you don't have to drive for 1 hour to the airport, wait for 2 hours for your flight, go through the whole security things. And well, most of the time, let's be honest, the flights are delayed, so you're never sure when you're going to arrive. It operates more like a subway system. There's a departure every 2 or 3 minutes. And as I said before, it's small vehicles. So just think of the subway, but at the scale of a country. You get to the station, you board the vehicle, at the same speed as an airplane, you arrive, if we're talking Toronto, Montreal, 45 minutes after departure, and you're in the city center of Montreal. A few information about Transpod. So the company was created almost 6 years ago now, so in Canada. We opened the first office in Toronto, and we also have an operation in Italy and France. So Italy, we're working mainly with our investors. There's an Italian industrial company. And in France, we have a few people. Well, actually, Dimitri is working from our office in France. They're working mainly on the technical developments of the subsystems. We are very proud, again, because we have a nice and strong project going on with the government of Alberta for a line linking Calgary and Edmonton. It's the first agreement we've signed in Canada, so that's pretty good. And it's a 3 steps project. I'll talk more into that later, so I'll give the details for the end of the presentation. We were the first one to publish publicly a feasibility study for a Transpod or Hyperloop line in general in Thailand. So that was 2 years ago now. The study was financed by a political candidate who wanted to include Hyperloop and new technologies into his platform. he did quite well in the elections. And most important thing to note here is that it's one of the first times that a politics were really pushing for this kind of technology to happen in their country. And we're also very much involved with the regulatory work at the so French and European level. We are also taking part in some initiatives in the US, and Canada should come soon, finger crossed. It's very important to make sure that once we have the product that's ready to be built and operated, that we also have the regulations in place. Otherwise, it wouldn't make any sense to have a product, but not being allowed to use it. So that's why we started this work, I think 2017 now. So it was very important to start very early because, well, these things take a lot of time to happen. What is it for? We have 4 main applications. So I said before, passengers and cargo, and we divided both applications, long distance, short distance, where the long distance applications make sense is very similar to an airplane travel, for example, or train travel, but much faster. Small distances would be stations along the way. And for that, we have, for example, what we call airport connections. It's nice to start with a smaller distance, even though we don't reach very high speed, but we can still demonstrate the feasibility of the technology over 10 or 20 kilometers before expanding the lines between cities. I won't spend too much time on the technical advantage that we have, because some of them are very sensitive and private information, but we are focusing most of our technology on the vehicle rather than the infrastructure. The vehicle is something that you will use a lot, like all of the time. The infrastructure is used only when there's a vehicle that's passing by. So it's much more important to put all the money and the fancy stuff on the vehicle. And it's also cheaper to build the line if it's very basic. So it's not very basic, but the infrastructure is a steel tube with some things inside that I can talk about, and concrete pillars. It's still a little bit expensive, but much less expensive than, for example, what was introduced at first in the Hyperloop Alpha document from Elon Musk, where he suggested to have electromagnets along the way. For some of the competitors, they're using maglev technology. Maglev, you're required to have electromagnets all along the line. And we know as a fact that that's super expensive. Actually, that's why there's only one maglev commercial line in the world, and it's not even profitable. So that's one of the key advantages of Transpod today, is to have a low cost of infrastructure. And well, of course, then the business case is better. And it's much easier to convince investors that our project may be feasible one day. And as I said before, so Alberta, it's one of the 2 lines we think would make sense in Canada, at least as a first. Of course, well, we would love to have a line doing Canada coast to coast. But so we're focusing on Toronto, Ottawa, Montreal. It's much more difficult to put in place because we're dealing with 2 provinces and it's a longer corridor. So we managed to secure a deal with the government of Alberta first. Calgary to Edmonton, that's about 350 kilometers. So the cost, the capex for the cost of the infrastructure is much lower than for a longer line, so it makes more sense. And our project is in 3 steps. The first steps, we're doing it now. It's a feasibility study to assess the, well, everything. The ridership, the cost of the infrastructure, and then putting all together all the calculations and seeing if the line would be profitable or not. Of course, if it's not profitable, then, well, that's the end of the project, and we'll find another location where it makes more sense. We really hope, and so far the numbers are pointing in that direction, that the line should be profitable. So the second step will be to build a test track, 10 to 20 kilometers, most probably between Edmonton downtown and Edmonton Airport. So we can test the technology and showcase to, well, investors, Canadian government, Alberta government, that the technology is working. And then the third step, once we have the feasibility study that proves the line profitable, and once we have the test track that proves that the technology is working, is to build the whole line and connect Calgary to Edmonton. So the whole, to get a little bit into details, but we're going to have a Q&A session at the end of this, so feel free to ask anything that we haven't presented. But the little bit details about that, the line would be Calgary downtown to Calgary airports, then Red Deer, then Edmonton airport, and then Edmonton downtown. So of course, we want to link the two city centers. We want also to be able to link the two airports to make sure that if you board a flight from let's say anywhere from the US to Calgary, then you can go to Edmonton in 15 minutes after landing in Calgary. And airlines, for example, wouldn't have to operate two flights, one to Calgary, one to Edmonton, because once the two cities are connected with a 15 minutes ride, well, it's like it's one big cities together. So that's a short, quick snapshot of the test track. Something very convenient also to say about Alberta and the connection between Calgary and Edmonton is that it's flat, and it's straight. So it's very easy for us to build a test track there. And finally, the roadmap about Transpod. So that's mainly to show you that it's a very long-term project. Basically, when I joined the company, one of my first questions, like for many other people I know, was when do we start to build? When we'll have a prototype or something? And then I briefly realized, well, no, this is something that's going to happen in a few years. It takes between 3 and 4 years to develop the whole technology. We have a few milestones that are the test tracks. So we are building a test track in France, a half-scale test track, the full-scale track, most probably in Alberta. And then we're aiming 2025 for the construction of the full line, and 2030, maybe 2031 for the first operations of the line. So be patient, we're working on it, but you still have about 10 years before we could ride the first Hyperloop line. And I mean like in a commercial way. So that's the overall presentation on Transpod. Again, the chat is open. Feel free to ask any question in the chat. We'll answer them at the end of the presentation. Dimitri is going to present you. Well, I'll let you do the introduction.
Okay. Hello, I'm Dmitry. I'm a Russian nuclear engineer, and I defended my PhD here in France on simulation of plasma guns. And now I'm working in Transpod and helping them with various kinds of physics and simulations. And this is my topic of the presentation, modeling simulations. So first I will introduce you to the terminology of my field. Then I will explain you the basic algorithm I need to follow when I want to simulate something. And finally, I'm going to give you a few examples from my work and from a world of simulations in general. So without further ado, let's start. So model is a simplified reflection of reality. When we talk about modeling in a scientific sense, it's a process of creating a model. And finally, simulation is an approximate imitation of a process. So basically how a model evolves in time. The ultimate goal of modeling simulations is to predict the future. And there are multiple ways of doing this. For example, there are models based on physical analogy, like on the bottom left picture, where the gravitational force between celestial bodies is represented by a piece of cloth. Then in the middle, we have another type of model. It's a scaled-down prototype. Here, it's a scaled-down version of a transport vehicle being exposed to an airflow in a tube. And on the right, we have a numerical model, which is fully inside of a computer. There are many other types of models, but I'm concentrated here mostly on numerical ones. If we talk about numerical models, there are roughly 3 flavors of them based on their physical realism and performance. On the left part of the spectrum, we have video games that are the least realistic in terms of physics, but they can run in real time almost on any computer. In the middle, we have visual effects that are realistic enough to fool our eye, but they're not necessarily realistic in terms of physics. And they require days and days or weeks of simulations. And on the right part of the spectrum, we have models for engineering and science. They could be potentially the most realistic ones if you desire them to be so. But the price to pay is the performance. Some of the simulations could last weeks, months, or even years to make. If we talk about like really complicated atomic physics simulations, for example. But regardless whether you want to make a video game engine or if you want to simulate backtrain, you would have to follow roughly the same algorithm. First, you need to formulate a problem you want to solve. Then you have to analyze the physical nature of this problem. Next, you should describe this physics using mathematical apparatus. Computers, they don't understand math right away, so you have to interpret your mathematics for a computer by writing the program. And finally, you need to use this program to solve the initial problem. So now let me show you a few examples on how I follow this algorithm from my work. This is a simple example about estimation of the tube temperature when it's exposed to sunlight. This is what I did a couple of months ago. So the question was, what is the maximal temperature the tube surface can reach? So here it's a line in Thailand. Terry mentioned about the study. So here are two tubes and there's sun and the sunlight hits the tube. And well, if the temperature is too high, then well, there could be a lot of nasty things like thermal expansion of the tube, or like maybe inside the capsule it will be too hot. So it was important to know what is the maximal temperature. And another question was whether we need to apply coating to the tube surface or not to reduce this temperature. Like, do we have to paint it white, or maybe it's okay just to leave it as it is? So first I analyzed the nature of the problem. Here is the cross section of the two tubes. Here's the sun and sunlight that arrives at a certain angle. Let's consider a smaller segment of the tube and see what happens there. So the sunlight arrives at the tube surface. Part of it is reflected, another part is absorbed. The absorbed part increases the tube temperature. At the same time, the tube is being cooled down by participating in heat exchange with the surrounding cold air and by emitting thermal radiation. So in the end, we have this energy balance between energy gain from absorbed light and energy loss. And this is really physics in a nutshell. Every term of this balance is a well-known physical law, and if we write it down, we'll get the equation we have to solve. I won't be explaining you each and every term here. All you need to know is that there is only one unknown here. It's Ts, the tube surface temperature. The rest we know. How to solve it? Well, we need to do some coding. So first, I rearranged the terms of this equation. I put all the terms with the unknowns on the left side and all the known things on the right side. And I got an equation that looks like this. It's a quadratic equation, and it could be solved graphically by finding the intersection between this curve, or the blue line here, and this constant, the red line here. This kind of intersection could be found using a simple for or while cycle in any sort of programming language. So after I wrote a program that finds intersections and basically finds the tube surface temperature, I've used it and determined the maximal temperature of the tube. Here on the plot, you can see how the temperature is distributed along the tube circumference. The red plot is for non-coated tube, and the blue one is for the tube painted white. And as you can see, the maximal temperature in the worst case, when the tube is not coated, is around 55 degrees, and when it's coated, it drops down to 35 degrees. So the answer to the original question, whether we should apply coating or not, was yes, we should, because it brings us this significant advantage and simplifies the decisions of other engineers in the team. Similar mathematics and physics is involved in computer graphics when we need to simulate how light reflects from surfaces. The next example is a little bit more complicated, and this is what I'm dealing the most in my practice with. It's about the gas dynamics or aerodynamics inside the tube. So let's consider a vehicle that moves inside the tube at high speed. While it moves, it displaces the air in the tube. So the air has to squeeze through this narrow gap. While the air squeezes, it accelerates to very high velocities, and it appears that there is a limit to this speed. The speed of this air is limited by the speed of sound. And in fact, this thing also limits the maximal speed of our vehicle. So the question was whether our vehicle can reach the promised speed of 1,000 kilometers per hour, or will we bump into the threshold of this air squeezing speed limit. And in order to find the answer to this question, we have to solve this system of equations. The most important ones are these three. They describe the velocity of the gas. They're called Navier-Stokes equations. And believe me, this system of equations is as scary for me as it is for you. So usually we don't even try to code the solution of the system by ourselves. All we do is we buy software that does the simulations for us. All we have to do is to build a 3D model, import it into the code, and run the simulation. And the results would look something like this. Let me interpret to you what happens here. So on the bottom left, we have lots of air pressure inside the tube. So when the vehicle moves from left to right, it compresses the air in front of it. So as you can see here, it's red. It's the high pressure. On the top left, we can see the air temperature. Because the air is being suddenly compressed in front of the tube, its temperature increases. So as you can see here, it's red. This is actually beneficial for us because in hotter air, the sonic velocity is higher. In this gap, the sonic speed is around 400 meters per second. Here on the right, we can see a plot of the air velocity in the tube. And in this gap here, it's green, so it's around 300 meters per second. And thus, because 300 meters per second is lower than the sonic speed under these conditions, which is 400 meters per second, we could claim that 1,000 kilometers per hour is indeed is not a limit, and we can go even faster. Navier-Stokes equations are quite heavy to solve, but due to advancement of computer hardware and software, now there are some games that solve these equations in real time. Like on the left, you can see cloud simulations happening, and on the right, there is a smoke simulation running in real time. Thank you for your attention, and now I'm going to give spotlight to Augustin, who is going to tell you about industrial design and passenger experience. Thank you.
Thank you, Dmitry. Thank you very much. Okay, let me share my screen. Okay, can you all see my screen?
Yep, all good.
Yeah, okay, nice. So I'm Augustin, I'm industrial designer, and I will present you what design brings to Transpod. So further, I'm 39, I'm from France, and I live in the Netherlands. I have a lot of experience in transportation industries. I started with car design for Jaguar, and then I quickly moved to railway industry. I joined the company Alstom for 15 years, where I designed metros, tramways, mainline trains, and high-speed trains for various locations in the world. Then I spent a lot of time creating their interior and exterior design from economy to business class concerning the railway industry. And then I learned a lot on how people move and what could be done to improve the experience. However, I had to work within the limits of a system that has been shaped centuries ago. There are a lot of limitations that can't be overcome due to existing infrastructures, technical constraints, and regulation restrictions. However, last year, I joined Transpod, where everything is possible, because we can change everything. We start from scratch, from a white sheet, and then we can change everything for the best. So, so here is how designers work. First, we analyze the current situation and people's needs and expectations. How will people live in the future? How can we make sure that our product will match their needs in terms of travel? So the goal is to make sure that our solution will be more than simply a faster way of moving, but also a better way of moving. Then we also create scenarios. We try to imagine all the passengers type going through any kind of situation to make sure we improve the way people travel. We had in mind all the inconveniences we can meet when we use trains and planes to make sure that we solve them. And to do that, we try to keep a holistic point of view. We consider the tangible part, the digital part, the infrastructure too, and then the vehicle, and also all the other modes of transportation that they are connected to. And then we try to map everything and to create the best passenger experience for the users. So from that analysis, from all the scenarios, we start conceptualizing and shaping our ideas. So it's hundreds and hundreds of ideas that are shaped simply using a pen on a paper at the beginning. And we integrate step by step all the engineering inputs provided by my colleagues, such as Dimitri and Thierry, that all the things I talked just before, and all the other colleagues. So the goal is to create the product that is the best solution for what it's supposed to do. So it's also important to give it, of course, an inspiring loop that communicates its functions and its values. For the interiors, the process is the same, with a greater focus on the passenger experience. We first need to develop the most optimized architecture that will allow a high level of personalization to meet all the needs of the future type of travels. We want to make sure that even when the system will be saturated of passengers, the experience will still be superior to the conventional transport systems that are existing now. Of course, everything you see here are preliminary work. The next step after the sketch, as you can see, is to create a 3D model that has improved a lot. But from what you're seeing right now, it has improved a lot, but you cannot see it right today. So step by step, we improve this 3D model, and we create some realistic images also, so because they are useful for our future partners, for also the future users. Then they can understand what we plan to do. They can get used to the future things, how they will travel. They can project the future of mobility. And then all the feedback we get from this communicating these images help us to improve our vision in return. Right, so if you have other questions, do not hesitate to write them in the chat, and I'll be available to answer to all of them. Thank you.
Kyle, the floor is yours.
All right. Hello. Can you hear me okay?
Yeah.
All right. Hi. So my name is Kyle Simmons. I work here at Transpod doing electromechanical engineering, prototyping, and testing. So people come up with an experiment or an idea or something they want to try. I put it together and see what happens. So one of the things I've been working on lately is the levitation system for our vehicle, because it, traveling down that pipe at 1,000 kilometers an hour to keep everything nice and efficient, we would rather not touch anything. So I like to think of the train, or the vehicle rather, as surfing on a wave of electromagnetic fields, or kind of surfing on a magnetic field. So what does that mean? How do you float something with magnets? So if you take a permanent magnet, like everyone's used to on their fridge or from various toys, all kinds of stuff, take a permanent magnet and put that near something metal, it will attract. It'll jump up towards that metal and give you a bit of a force. It has some lift to it. But something you'll notice is there's no kind of magical place you can put this near the metal where it'll just float. It always wants to stick. So, all right, what if we had a magnet where we could change the strength of the magnet? Maybe then we could make it float. So I have here some electromagnets that are a lot like if you take some wire, maybe you've done this in physics class or at home following a video tutorial. You take a piece of metal or even just a bolt, something like this, wrap a bunch of wire around it and hook it up to a battery, and you can pick up paper clips or various things. What's cool about that kind of magnet is you can adjust in real time how strong it is. So I have here an electromagnet hooked up to a power supply, and I will see if I can adjust that power supply to make this magnet float. And so on. So I could adjust that all day. I could try different amounts of power and different distances, and it's never going to hover there. And that's because it's a system that's inherently unstable. It's a little bit like trying to balance a stick on end, a broom handle on end. If you just stand it there, it's going to fall over. You have to make little adjustments all the time to keep that upright. And of course, I'm not very good at it. So what we need is something called a control loop. So a control loop is a lot like when you're in the shower, setting the temperature for the shower, and the water's too cold, so you open up the hot water tap to get more heat. And it's like, oh, okay, well now I've opened it too much, it's too hot, so turn it back a little, so you get a little less hot water, and there's less heat, and you keep adjusting until you get where you want to be. And the basic process you're following there is you're using your hand to sense or measure how hot the water is. You're thinking about what needs to happen and then making an action. And that's basically what a control loop does. It takes an input, it does a little bit of processing, and then it has an output, it has an action, kind of like, yeah, setting your hot water tap or the little movements I make to try and keep this ruler stable. So putting all this together, we end up with an apparatus that looks like this. So this has two electromagnets on it, and it has two sensors at the end, these little blue circles, these wonderful little blue things. So what those are kind of like little eyes that all they can see specifically is how far away a piece of metal is, or in this case, how far our little vehicle is from the rail. So if I turn this on, and I put this up close to the rail, it will actually keep itself afloat. Now, really, it needs a few more magnets and a few more sensors to keep it totally stable, so I have to hold it here at one end. But I hope you can just see the light kind of sneaking through there, that gap. So this is not touching the rail at all. There's actually about 1 millimeter between the vehicle here and our rail. So what's really cool about this is it means, because there's no contact, there's almost no friction. So that allows our vehicle to move really efficiently. And of course not have any parts that are touching so things don't contact. So my job here really was to make sure that those little blue eyes, those sensors, do their job quickly and stable enough so that the vehicle is safe and has a smooth ride, and a whole bunch of other things. Just testing that little sensor can tell us a whole lot about how the system is going to behave and whether that sensor is good or not. So obviously we've gotten levitation, our sensor is good, we can take it to the next steps. You can do all kinds of prediction and calculations about a system, figure out how much power these magnets can draw, how quickly our power supply can vary them, etc. But you really don't know how the system is going to behave until you build it. Yeah, so that's kind of my fun, crazy job here. I'm a little bit like a mythbuster. We come up with ideas or things, like I said, and I've actually got to bang it together and see if it'll work. So that's one thing I've been working on. Yeah, that kind of concludes the meat of the presentation for me. Does anyone have any questions?
So Albert, I don't know how you want to do this, but yeah, people can ask questions in the chat, or if we can keep it nice, just unmute yourself, ask the questions. Or yeah, there's the first one. That's for Kyle. How many sensors per magnet?
So in this case, it's one per magnet, but if you have larger arrangements of magnets and sensors, it's not always one-to-one. Sometimes you have a few sensors controlling many magnets together. But in this case, for our test apparatus, it's one-to-one. Any software to simulate that PID loop? So in this case, this one we just hand-tuned. And this one, actually, yeah, it's great that you're bringing up PID. Yeah, this one is, this is PD. This is pure proportional differential, so it's proportional and then differential for the dampening, so it doesn't dance up and down. No integration. Most challenging part of your job for me, it's yeah, really having to be inventive sometimes, because some of the stuff that we're trying out, it's kind of new, it's kind of different, it hasn't been done before. So we're kind of in new territory sometimes. And I'd say the second most difficult thing for me is actually making sure everyone's on the same page and communicating. Communicating is tricky. Communicating is tricky, which leads into something I would say about people asking about well, how should I get started? What things should I be educated in and all this? And there's all these technical answers. A big one is English. Make sure you can communicate with people. It's a big part of any job really, but even a technical job where you're banging stuff together with a wrench and grease and getting dirty, you still need to be able to communicate.
And for me, the most challenging part of my job in specifically is mathematics. Because sometimes when you have like some high-level mathematics, some different systems of differential equations, and it's sometimes hard to wrap my head around it, even though I studied it. But yeah, so my advice: be better in mathematics, as good as you can.
Kyle and Augustine, you've answered my question before I was going to ask it. It's almost like you knew I was going to ask it. So I'll ask a different question for you. Can you explain to folks the different safety features and fail safes that are in place on this technology? Yeah.
So let's see, I guess one I could do from the technical stuff for safety. Yeah, we have many redundancies, a lot of redundancies, a lot of systems that check other systems. There's a lot of backups and control in computers. Also things like along the infrastructure, along the pipe, we have the ability to repressurize very, very quickly. The vehicles constantly do monitoring and checking of the pipe to make sure everything's healthy. So the system is constantly measuring and monitoring itself. And we're also working with a whole bunch of companies that do technical standards and establishing new standards as well, but looking at what standards are out there to make sure things are as safe as possible. All the way down to material sciences. Yeah, we're kind of exploring everything. But a lot of it's, yeah, redundancies and making sure safety systems like ways to get air back into the pipe and various things are all designed very, very carefully. And we're working with a lot of people to get all the details ironed out as early as we can.
Are you working with regulators as well on that? So say like the body Technical Standards and Safety Authority, are they involved in any of your work?
Companies specifically or entities specifically, I couldn't list, but Thierry might know some of those. But yeah, companies like that, companies that do transportation or that do electrical systems that are life critical, things like this. Companies that are and entities that are very experienced in this, we are in communication with.
Yeah, you're right. Most of them are in Europe, France mainly at the moment, because that's where the most of the work has been done in terms of regulations. We look forward to starting working with some companies in Canada as well on that.
We have a couple other questions here. Is there a length at which you might start experiencing curvature in your magnet arrangement, and how would you mitigate that?
Kyle, that's for you, that one. I can take the next one on turns. But...
curvature. Oh, possibly curvature for turning radius. If that's what you mean. So that if the magnets are super long, they have to be curved so the vehicle can curve.
I can clarify that for you, Cal, if you want.
Oh,
Sorry,
yeah.
I realize it's not. You just talked about communication, and here I am throwing an ambiguous question out to the group. No, I mean, if you start stacking your magnet arrangements together, at one point, weight-wise, are you going to experience kind of a curvature, you know, where your center point of your arrangement might not be in line? So, are you accounting for that? Or are your arrangements going to be short enough that you're not going to experience that kind of potential extra force in the middle, I guess, of the arrangement?
The geometry works out that we don't need to worry about that too much.
Okay.
But both between like the levitation distances and the way we're scaling things and making sure we have certain grades of curvature in the pipe. Yeah, it's not something we have to worry about too much. Interesting question, actually.
And for the next one, how do we plan to do turns? So you have to think of the vehicle, it's circular as an airplane. So where an airplane relies on the weight of the air, so to speak, our vehicle interacts with the tube with electromagnets. And so it's all a matter of controlling the magnetic fields and the intensity of them, and to be able to maneuver the vehicle around the three angles. So making sure we can go forward, backward, but also rotate, like if you see my pen, inside the tube, so that we can take into account the centrifugal force, and then that's how we operate the tube, the turns, sorry, in the tube. And the vehicle is short because we want to make sure we can have a lot of departures, so every 2 or 3 minutes. On the contrary to a train, when you have to wait for 200 or 300 people to board at the same time. So that the good advantage is that the vehicle is short, and so we don't need to have very high curvature radius. Even with low curvature radius, it depends on the speed, of course, but we are able to do some nice curves. The next one, what's the relationship between the air pressure and electric magnets on the train's velocity?
Okay, so we do have a little tiny bit of air pressure in the pipe. It's not pure vacuum. And actually the drag on that is sort of what Dimitri was talking about. It's not super high. It's there, but it's not super high. So we don't have to worry about it causing that much drag. If that's what you're talking about, like how much power do we have to dump into the electromagnets extra, maybe because of air resistance? Yeah, it's not super high.
And how do we control the pressure? We have a few vacuum pumps connected to the tube. So there's a few configurations possible. Big vacuum pumps every 5 kilometers or smaller ones every 100 meters. I'm just giving random numbers, just to make sure that there's no confusion here. But there's a few technologies involved, and it's all, well, it's again a matter of loop. We have sensors controlling the pressure in the tube, and if the pressure goes like much higher than 100 Pascal, that's one of our target pressures, then we activate more vacuum pumps or make them turn like faster, so we can absorb the air until we get back to 100 Pascal, and same way otherwise. It's all a matter of loop and control and actions. From Amir, how big is our company and how many employees roughly? So we have about 25 employees today, between Canada and let's say Europe. So mainly France, but as we say, well, it's COVID, so everybody's working from home. Augustin is in the Netherlands, for example. But yeah, altogether it's about 25 people working for the company, excluding all the partners that are working remotely on several projects with our teams.
Great.
And oh, that's what is important. What happens if there's a vacuum leak? So of course the tube has to be airtight, because that's the most important, one of the most important part of the technology is the low pressure in the tube. If it's a small leak, one question we get a lot is, what if someone shoots in the tube and there's a small hole? Especially, we get that question a lot in the US actually. So if there's a small hole, there's a small air leak, it's not a big deal. Maybe you remember there was a small hole in the International Space Station. I think it was 2 years ago. And they realized they had a few days before getting out of air. So it's the same for us. If it's a small hole, there's an air leak, and we just have to make sure that the vacuum pumps can absorb that air leak. If it's a bigger one, then let's say the worst scenario, touching wood, is that there's a break, a truck drives into a pillar, for example, that the tubes are not aligned anymore, and there's a huge entry of air in the tube. Then we have security system in place. That's where they enter into play. We can close doors at regular intervals in the tube to isolate certain sections. So all the sections that are isolated and far from the incident, well, would stay safe under pressure. We stop the whole system, and we can work on the section that has an issue. Long story short, if there's any issue, we have a system that's able to repressurize the tube in 15 to 20 seconds. So the vehicle stops, put back the pressure in the tube, everybody is able to escape the pod safely and go to an emergency door. There's going to be doors from the tube to the outside every kilometer or so. So people don't have to walk too much, and they will be able to get in the free air safely. And Carl, you may want to talk about the next one, but it's basically redundancy. What happens if one of the sensors stops working?
Yeah, exactly. Redundancy and multi-mode sensing. So we would have multiple different types of sensors kind of staged as well. Like these tricks you can use actually to use the coil like this as a sensor as well. So it can do detecting and levitating, and there's other ways to do this as well. But yeah, basically staging of redundancies. So the system's over-constrained. We could lose easily half the sensors on the system, and we would still be able to control everything with pretty good accuracy.
And Roman, yes, you're right. It's going to be an automatic system. So there's no driver. First, because it's going too fast, and like any driver could not have enough reaction time to react to whatever is happening. Electronics and computers are much faster. So they will be supervised by human beings, of course, but the whole system is automatic. So all the pods, the vehicle in the tube, have their speed synchronized with each other. So if 5 pods ahead of yours, for example, the pod is slowing down for whatever reason, well, the information is transmitted and automatically we forward it back to any pods behind that first one. So they all adjust their speed and everything can be able to like work smoothly in the tube.
We'll have to make the next one the last question, I think. We're running just a little bit short on time.
Alrighty.
So if there's an emergency required short notice halt, how many passengers, no, sorry, how are passengers protected of high G forces? So if there's an emergency brake, well, the emergency brake is calculated in the way that there's not too much G force applied to the passengers. So seatbelts or not, that's something being discussed with the regulatory authorities. Like for example, in buses, there were not seat belts until a few years ago. Now it's mandatory. Well, not in every country. So that's totally up to the regulator to tell us if it's going to be mandatory. And of course, we'll do simulations as well. First on computers, then with actual bodies, and small scale, then full scale. I mean, not human beings, but mannequin, to make sure it's safe for people. There's a lot of questions. Augustin, I'll talk about the rivalry. I'm not too Canadian enough to understand the Oiler Flames competition. It's just, long story short, it's not a setting, it's more an opportunity. We haven't listed all the cities in Canada and say where we are going to build our line. It's more open discussion with several locations, and it turns out we had a good match with the city of Calgary and then the government of Alberta. They were interested in having our lines there, especially because they need big investments now to support the economy of the province. So that's how it got all along, and it's always easier to work with some people who wants to work with you than trying to convince people who don't care about what you're doing. And that's kind of what happened in Alberta. They were interested. We were looking for a location, and it all aligned well, which is why we're having a good collaboration today.
Great. Well, we'll have to call it at that. Thierry and your team, thank you so much for presenting. Great job as always. Very informative, very interesting. And
Sure.
If everyone can hold on for a second here, we'll have a quick poll. And yeah, answer if you can. Thank you.
Yeah, and last thing, any question we have not answered or any question you would have in the next hours or days or like whatever, feel free to send an email, info@transpod.com, or you'll find more information on the website as well. But we answer every email we receive, so feel free to ask any question you might have.
About the travel experience with the external view, it was, I replied before. You know, it says that the tubes won't be transparent, therefore the pods won't be transparent. So there's no external view per se, but this opens many opportunities in terms of passenger experience and design that cannot be seen in common transportations up to now. Of course, things will be decided and ordered by the customer, the one that operates the pods. But so it can be to something basic or something completely electronic, where it's I mean, everything is possible in that case. You know, you can have augmented reality, for example, but this depends mainly on what the customer wants to offer to his passengers. Regarding that, remember also that the duration of the trip will never be like a 5-6 hours trip like what you can have in a train or in a plane, for example. It will be always short trips due to the speed of the travel. Does it answer to your questions? Okay. Thank you very much, everyone.
Thank you.
Thanks again for joining us. It was great seeing you again.
Bye.
Bye.